Hi everyone. We're going to do two laws today. We're going to talk about Gay-Lussac's law, and then we're going to do the combined gas law. And that's sort of, like the name implies, putting it all together. But first we're going to start off with Gay-Lussac. So his name, Joseph Louis Gay-Lussac, again, a Frenchman. I think I told you with Charles' law, there was a lot of the gas law information came out of France at this time because of the hot air balloon travel, which led to some really interesting science going on. It's a good indication of how we have, the politics or the political climate of the time or societal implication, how that influences what science is going on. Mr. Allard, if any of you had him for history, he would be very interested in that. Probably Mr. Mike too. So 1778 to 1850. This is when Gay-Lussac, his dates, birth and death. He studied gases for his career. What's interesting about him is he would often take appointments for financial gain. So weirdly, this was not actually the case initially. A lot of scientists, sort of science was more their hobby, or they had to be independently wealthy. So he was one of the first ones who wanted money for his research. So he was criticized for this as he was turning away from the path of sort of what's known as pure science here. So why or how science sort of doesn't belong to anybody, so nobody should benefit financially from that. And I mean, you still see that today. You have all kinds of people who sold, like insulin, for example. Canadians discovered insulin, how to create it, and they sold the patent for it for $1 because they didn't think they should benefit from that. So there still is an element of that in science, which I think is quite lovely. So Joseph Gay-Lussac used volumetric analysis, and so he's one of the first ones who did this here. So he was the first one who published terms like burette, pipette, and titrate. And I don't know if you ever noticed, any of you who have taken any French, these are very French words, right? So that's where they came from. This law, so his law that he is credited with was first initially discovered by Guillaume Amonton. So like some of the other laws, though, he would have built off other people's research, and then that's why we have it as his name here. And we notice here that Amonton was actually quite a bit earlier than Gay-Lussac here. Anyways, that's just the history, the background for you. You won't need to really know that in terms of memorizing anything. So again, now Boyle we talked about was pressure volume, Charles temperature volume. So we got our last two variables with Gay-Lussac here. So he studied pressure and temperature, and so he determined that the pressure of a gas varies directly with temperature, and that is again in the Kelvin temperature scale when the volume is kept constant. So like the other laws, they have to have the third variable being kept constant here. And so if we were in class, I would get you to visualize this, and I would get you to hold in your hands an imaginary balloon. So maybe just put your pen down and hold your imaginary balloon here. Except this time your balloon is made of steel, which means it cannot change. It can't get bigger, it can't get smaller. I guess I could have just gone with a container, but for some reason we're going to go with the balloon here. So a steel balloon. Now, if you've got gas particles in here, right, you've got your gas particles. So you've got at a certain temperature, you've got a certain amount of pressure, right? Now, if we start increasing, and I just like to do this so I can change, where'd it go? Hold on. I can change the color of my pen. Ooh, that's my fire. That's horrible. That's a flame. So if we start heating the temperature, what's going to happen to the gas particles in here? They can't expand because this is a steel balloon, which means the volume cannot change here. So what's going to happen, they're just going to start moving faster and faster and faster here, and that's going to create more pressure. And again, this all links back to kinetic molecular theory, right? So the particles are in continuous random motion, and they're influenced by how much energy they're supplied, heat being energy, of course. So we know then that from this, pressure varies directly with temperature. And again, we're going to go subscript K there just to show that that's the Kelvin temperature scale. All right. So we're just going to work through an example here. So if a sample of gas is found to have a volume of 12.0 liters at STP, calculate the new pressure at 128 degrees Celsius if the volume is constant. So if the volume is constant, that means this is not going to change. This is a 12-liter container. It's constant. You don't need to worry about that. We're only dealing with pressure and temperature for this law. So we're going to go through, and I would write your variable list again. So P1, T1, P2, T2. Now, often people get a bit confused with questions like this because it looks like I didn't give you initial conditions. But one thing you have to note, STP. So you need to remember, what does STP mean? And what is the pressure at STP? Yeah, so it's going to be 1 atmosphere or 760 millimeters or 101.325 kPa. I'm going to use 1 atmosphere. What is the temperature at STP? 0 degrees Celsius, but I'm going to change that into Kelvin, so 273.15 Kelvin. Pressure 2 is what I'm looking for because it says calculate the new pressure. Temperature is 128 degrees Celsius. So if I change that, I have to change it to Kelvin. So 128 plus 273.15 is going to give me 401, so 401.15 Kelvin. So now I've got all the information that I need. And now I can just sub in to my equation here. So again, oh, you know what? I didn't give you the darn equation. Silly me. So this is going to be exactly like Charles' law. So P1 over T1 equals P2 over T2. Okay, so that is your law there. So you can make a note of that. Sorry about that. Okay, so moving back here then, P1 over T1 equals P2 over T2. Now, I'm solving for P2. So again, I'm going to use that little trick, that rearranging trick to bypass the algebra here. So P2 is what I'm looking for. Running out of space, I'm just going to go up here. So P2 is going to be equal to, and then everything on the diagonal goes on the bottom. So T1 goes on the bottom. Everything left over goes on top. So P1, T2 goes on top. So now if I sub in, I've got 1 multiplied by 401.15 divided by 2, I can't seem to go there, 273.15. Sorry, it's cutting off there for me. So if I work this out then, so I'm going to go 401.15, obviously multiplied by 1, divided by 273.15, and I get an answer of 1.468606, etc. But how many sig figs can I have in my answer? I'm going to use this data here, the 128 degrees Celsius. That's the only real information that I'm given for significance. So your answer then is going to be 1.47. So I'm going to round that, and your unit, atmosphere. And again, we want to just make sure that that makes sense. I started out with 1 atmosphere. The temperature increased quite a bit, so I should see quite a large increase in pressure, which I did. So there's your answer there. Okay, I'm only going to go through the one example because it's really similar to what we did with Charles' law and Boyle's law. So you can try those now. The combined gas law is what we're going to look at next. So this is when we literally just put them all together. So first of all, we looked at Boyle. And then what was the relationship between pressure and volume? We had pressure varies with, and then it was, 1 over volume. So that was our indirect relationship. Next, after Boyle, we went to Charles. And for Charles's law, we had volume varies directly with temperature. And then thirdly, what we just learned, Gay-Lussac, and he was pressure varies directly with temperature. So if we look at those three laws, if we were in class, I would get you to see if you can figure out what the combined gas law is. You can pause the video if you want. So these are your variables. You're going to have P1, P2, V1, V2, and T1, T2. So see if you can put those into an equation that makes sense. It's kind of interesting. Some people definitely would be able to do it. So if you want to, just pause the video here and try it. If not, we'll just keep going here. So essentially, what the combined gas law ends up being is P1 V1 over T1. P1 V1 over T1 equals P2 V2 over T2. And if we look, we can actually find the three laws in here. So I'm going to do that. So Boyle's law, for example, is right here. P1 V1 equals P2 V2. Charles' law is going to be this one. V1 over V2 equals V2 over T2. And then we have our last one here, which is, oh, different color. Oh, no, I did. Is going to be Gay-Lussac's law here. So we've got our three laws all combined here, but make sure you remember what this actual law is. P1 V1 over T1 equals P2 V2 over T2. So that is the combined gas law. Now we're going to practice rearranging the formula. If you'll remember, we're going to use that little trick here. That's going to come into that's going to be very helpful to you now as the formulas get more complex, right? So let's do P1 V1 over T1 equals P2 V2 over T2. So let's say I'm asking you to solve for P2. Now, you have to do quite a bit of algebra to rearrange that, so that's why this trick is so handy. So if you want to solve for P2, oh, why is it dead? There we go. If you're going to solve for P2, we're going to circle what we're looking for, right? So P2 is going to be equal. Now, everything on the diagonal goes to the bottom. So T1 goes to the bottom and V2 goes to the bottom because those are on the diagonal. Everything left over, which is this stuff here, that goes on the top. So P1, V1, T2. So it's rearranged nice and easy. You can easily solve for that. So let's try it again. So P1 V1 over T1 equals P2 V2 over T2. So now let's say I wanted you to solve for T1. So let's solve for T1 here. If you're solving for T1, you're going to circle what you know. So again, just pause the video and see if you can do this. Okay, so solve for T1. You're going to draw your diagonal. So T1 is going to be equal, and then everything on the diagonal goes to the bottom. So P2 V2 goes to the bottom. P1 V1 T2 goes to the top. Now, every time people mess this up, they mess up rearranging their formula, and it's just such a crummy way to lose marks, right? So just make sure that this is solid for you. Okay, we're going to work through an example here. Again, please write yourself a variable list. It really helps. So P1, V1, T1, P2, V2, T2. Incidentally, I did order myself a better stylus because this one's pretty sloppy. It's just a thick point, but you guys are finding this too. Amazon is totally backed up. Canada Post is backed up, so I have not received it yet. Okay, anyways. If a gas has a volume of 25.0 liters, so right away, 25.0 liters, and 25 degrees Celsius. So I'm going to go ahead and change that right away because I'm going to run out of room here. So you're going to go 25 plus 273.15. And so this is going to be 298.15 Kelvin. And 1.25 atmospheres of pressure. Calculate the volume. So calculate volume. So that's what I'm looking for, V2, at 128 degrees Celsius. So again, 128 plus 273.15 is going to be 401.15. 401.15 Kelvin and 0.75 atmospheres of pressure. So now I've got my 5 variables. I'm looking for the 6th. So now I can go ahead and write my equation. P1V1 over T1 equals P2V2 over T2. I am looking for V2. So I'm going to rearrange my equation. Oh, sorry. Everything on the diagonal goes to the bottom. So P2 and T1 goes to the bottom. Everything else goes up top, P1, V1, T2. I'll let you sub in the values here because I'm out of room, but then you're just going to do the math here. So it's going to be 1.25 multiplied by 25 multiplied by 401.15 equals, and then divide it by 0.75 and divide by T1, which is 298.15. Okay, so V2, you get an answer of, and I have to look at my sig figs. Your sig figs, because of this one, are only going to be 2. So you're going to have 2 sig figs. So your answer is 56. And the unit is going to be liters. So 56 liters. Good? Okay, again, I'm only going to do one question of these. They're all fairly similar. The one thing you have to watch out for is little tricks in terms of the language of the question. So that would be something you'd look for. Okay, so exercises 6 and 7 are assigned for today. Now, tomorrow we're just going to have a Zoom meeting, and this is for any questions that you may have. I liked this little meme here. I was like, is this why they don't want their cameras on? Is this because this is what you all look like? Yeah, you don't have to have your camera on, although I do find it easier to teach you if you do have your video on, but whatever, that's your decision. So we're going to have the meeting. I think we're going to have it at noon. Oops, that's noon. Mainly because 2:30 on a Friday doesn't work. So let's try noon and see how you do. Other than that, there'll be a quiz on Monday. Okay, so the quiz will cover all of the gas laws. So the Boyle, Charles, Gay-Lussac, and the combined, but it will only be calculations. So you don't have to memorize any of the historical stuff or anything like that. Okay, thanks guys.